Okay, day one, graphical and numerical limits. The general idea of a limit is to describe the behavior of a function close to a certain input. If the function is defined, this could be very easy. You could maybe just plug it in, but sometimes functions are undefined, and sometimes you have these piecewise branches that are happening, so finding a limit can become complicated. Now, if you have a graph, or if you can actually make a graph with a calculator easily, then it's easy to be able to tell what the limit is just by observation. So we're going to first look at this complicated graph that has a lot of different things going on and analyze it step by step. So you can see that in this graph, if we were to approach the number 0 from the left, 0 minus means we're letting the x's get close to 0, but we're just going to be a tad to the left. So inside of the picture, that would mean I'd coming along this part of the graph towards that point, and I can see that the output is going to be 3. If we approach 0 from the right-hand side, that means we're coming in this way, and I can see that there the output is also equal to 3. This means overall this function is kind of chill, right? It's kind of settled down near 0. It's approaching 3 from both the left and from the right-hand side. So overall, we would say that the limit is 3. And finally, in this particular case, we can actually see that the actual output, right? F of 0 means I'm actually sticking in 0, and that would also provide 3. When these kind of conditions come together, we call this a continuous function. A continuous function used to be I can draw it without lifting my pencil off the paper, but now more formally it means there's a limit and it exists, and the function value actually equals that limit. So if I scroll down to the next set of problems here, we have limit as x approaches -2 from the left. So here's x equals -2, so now we're traveling along this part of the graph, and I can see that the output is getting close to -1. On the right-hand side, if I were instead to come along this part of the path, I could also see that the output continues to be -1. Therefore, overall, again, the function's pretty chill. It's predictable. It seems like the output is close to -1. However, in this case, we can see the open dot, which indicates that the output is not actually equal to -1, but is instead equal to +1, as we can see up here by the closed dot. So this function is not continuous, but it has a very special kind of discontinuity that we call a removable discontinuity. Call it removable because we could hypothetically pick up that dot, that solid dot, and move it down to the open dot and sort of complete the picture. Okay, now I'm going to have to scroll down to the next set. So let's shrink ourselves a little bit so we can see 9 through 12 and the graph at the same time, and also 13 through 16. But now we have limit as x approaches 2 from the left, and so here's 2, and as I come in from the left, I'd be coming in on this part of the path, and I can see that my output is now approaching the number 2. As I approach 2, but from the right-hand side, that means I'm coming in towards here, and I can see that my output is getting close to 1. Therefore, overall, we say that the limit does not exist because this function is not chill. It's approaching different numbers depending on whether you're on the left or the right. However, f of 2 does have a value. The closed dot there indicates that we're getting that right-hand side branch and we're getting a 1 as an output. When a function physically jumps to another spot and there's no way to fill it in, this is what we will call a jump discontinuity. Jump discontinuity. And then as we approach -1, we can see in this function here that as we approach -1, from the left we'd be coming up this part of the graph, flying off towards positive infinity. Then, if we look at it on the right-hand side of -1 instead, we're still hitting this flying off to positive infinity. And so you might say overall that the behavior of the graph near -1 seems to be positive infinite. But what's interesting about this case is that f of -1 itself, there is no closed dot on that vertical line. Right? We have sort of an acting like a vertical asymptote here, and so this would be undefined. There is no value. We sometimes refer to these as infinite discontinuities. because they are flying off to infinity on one of the ends. So it's a little bit different than a jump. It's not something nice and finite. It's actually growing quite large. Couple extra examples down here with our limits towards the end behavior. You can see that the limit as x approaches negative infinity. As I travel far and far and far to the left, it appears that the horizontal asymptote would allow me to be getting closer and closer to 0. So we'd say the end behavior, or the limit as we go towards negative infinity, is 0. And then on the right-hand side, I can see that the function's bumping up and down and up and down, so it never really settles down. It just keeps bouncing up and down. So this is going to be a does not exist. Okay, so that was the graphical introduction to what's going on here with limits. Now, if you have a calculator active anyway, we can try plugging in numbers that are really, really, really close to a particular output. So I'm going to now use the calculator to help me find the outputs of this function really, really, really close to the number 5, and use that to infer what the actual value of the function is at, or not at 5, but near 5. What is the limit as I approach 5? So I'm now going to turn on my calculator. And a procedure that works well here is I'm going to use my set theory brackets and type in all of my numbers. So I get 4, 4.9. Actually, before I do this, I'm going to set my calculator into a rounding mode. I'm going to now program into my calculator 4, 4.9, 4.99, 4.999, 5.001, 5.01, 5.1, and 6. So this is now in my calculator as a list. So if I want to figure out what the value of that limit expression is, I can go alpha F1 and type in answer squared minus 25 over answer minus 5. And this is going to take every entry from the list and perform that operation to it. If they come out in fractions and you don't want them in fractions, like we don't because we're trying to see what the impression is, just change it into decimals and see that we are getting 9, 9.9, then we get a 9.99, and a 9.999. And as I scroll over to the other side there, I can see that the other outputs were giving me 10.001, 10.01, 10.1, and 11. And so as I'm getting close to the number 5, I know I can't stick in 5 because I'd be dividing by 5, but it appears as though I'm looking at something that's going between 9.999 and 10.001, and that means that the value of the limit, the behavior, is chill, it's settled down, and it's giving me the result of 10. Maybe I should make this big again. 1 second. Yeah, nice. Okay, how about sine of x over x? What's happening to this function? So this time, let's again make a list, and in that list, we'll stick in -1, -0.1, -0.01, -0.001, and then go on the positive side with 0.001, 0.01, 0.1, and 1. There's my list. Let's calculate the sine of the list divided by the list. Whoops, I'm going to use ands. Sine of the previous answer over the answer. So we can now see that we're getting 0.841, 0.998, and then effectively 1 and 1, not exactly, but effectively. And on this side, we're getting same numbers in the other order, 1, 1, 0.998, and 0.841. So overall, can we predict what's happening here? It seems to be chilling down, and we're getting an answer of 1, and that appears to be the limit. Another example, let's do the x plus 3 over the absolute value of x plus 3 as we approach -3. Okay, list -4, -3.1, -3.01, -3.001, and then on the other side we'll go -2.999, -2.99, -2.9, and -2. Make a fraction again, and we'll go answer plus 3 over absolute value of answer plus 3, -1, -1, -1, -1, but then on the other side we get 1, 1, 1, and I bet you the last one's 1. And so now we can distinctly see that on one side we're approaching -1, but on the other side we're approaching a different number. And so there's a jump that is happening here. This is going to be a D and E because it's not predictable. How about this example? Same list as a previous list that we did, so let's go up and grab that list. That was this one. That's now my ands, and so I can just go in and go alpha F1, and perform 1 over 2 plus the ands minus 1/2 over the answers. Let's change those into decimals. And it looks like we're getting -0.5, -0.263, -0.251. Continuing on, looks like a -2.50 at both of these. -2.50. And then on the other side, 249, -0.249, -2.3 or 0.238, and finally a -0.167. So again, close to 0, seems to be getting close to -0.25, and indeed the answer to this one is actually -1/4. This problem's nice because it didn't fill in the table for me, so therefore I can just plug in whatever numbers I want, whatever ones I think would be appropriate to try to work this out, since it's just asking us to kind of find the limit. So in this case, I guess if I need a number just a little bit to the left, I'll plug in 3.99999 or something like that. So I would get 5 divided by the absolute value of 3.999 minus 4. Seems to be giving me an answer of 5,000. And then on the right-hand side, if I plug in the same problem but put in a 4.001, that's also giving me 5,000. That's interesting. That means maybe the limit would be 5,000, but I'm a little suspicious here because getting a number like 5,000 is really weird out of a function like this. So let's go back and see what happens if we go 3.999 with one more 9. Oh, it's not close to 5,000. Now it's close to 50,000. So what this is indicating is that this is some kind of graph that has an asymptote, and it's flying off towards infinity on both of these sides. So this answer is positive infinity. Final problem for this lesson. Here we didn't give you a chart at all, so you just have to think of a number that you know and love that's close to 0. And let's do one on the left. Let's do -0.0001. And then on the right, we'll do positive 0.0001. You could plug in more numbers like we did in the charts above to get an impression, but as you start to get better at these, more versed in them, you start to understand the behavior near this point just by plugging in some 1 or 2 numbers. Let's go see what we're getting here. So I have 1 over -0.0001 minus 2 over -0.0001 squared plus -0.0001 And as I close that off and press enter, it looks like we're getting an answer of 10,002. What if I go back and I delete the negative sign? What's going to happen if I delete the negative sign out of there? Oh, now I'm getting a value of negative 9998. So as we saw in the most previous problem, this is probably some kind of infinity, but on the left-hand side it's flying towards actual infinity, and on the right-hand side it seems to be flying towards negative infinity. So is this chill? Are we getting an actual output, or can we predict the output? The answer is no. This limit, therefore, does not exist.